While David Lewin first proposed applying the discrete Fourier transform, the DFT, to music theory in 1959, the idea was not significantly followed up on for years. In the meantime, the DFT has been used with great success in digital signal processing and also has applications in fields such as weather analysis, data compression, and image processing. Ian Quinn reintroduced the DFT to music theory in 2007 using the metaphor of a Fourier balance to illustrate its relationship to different harmonic qualia. Since then, theorists have used the DFT to model harmonic motion, set class similarity, and meter, to name just a few applications. In 2019, Matthew Chu applied the DFT to the macroharmonic properties of larger musical excerpts using a sliding window. My work builds upon this apparatus, and I am very grateful for our correspondences and discussions on this research. I use the Music 21 Python module to interpret the pitch classes of an encoded musical score through the discrete Fourier transform. This methodology offers a broad view of the backgrounded scales and pitch class collections of a piece, what Dmitry Tomashko refers to as macroharmony. I have selected two excerpts in which the composers are very frugal with their pitch class collections, one in a tonal idiom, the other atonal. The exposition of the first movement of Mozart's String Quartet No. 4 in C major, K157, is almost entirely diatonic. The theme from Messiaen's Theme and Variations for Violin and Piano adheres strictly to two of his modes of limited transposition. These constrained and, in the case of Messiaen, highly symmetrical harmonic vocabularies are well suited to demonstrating the DFT's methodological strengths as they pertain to score analysis. The Fourier transform is a mathematical function that decomposes an input signal into its constituent sinusoidal components. The discrete Fourier transform uses an array of discrete numbers, as opposed to a continuous signal, as its input. This makes it possible to apply the DFT to the pitch class content of musical scores. The counts of pitch classes become the input array. Our array will be 12 positions long, one position for each pitch class. The output of the DFT provides information about the aural qualities of the input, which roughly correlate with the qualia of the familiar interval cycles. Is it chromatically clustered? Is it more whole tone sounding? Is it fifthly? Applying the DFT to macroharmonies allows us to see a broad overview of a composition's sound. To illustrate the output of the DFT, imagine a circle containing 12 equally spaced nodes. If we tie our 12 pitch classes together onto an elastic string as if they were beads and stretch it around the circle once, each pitch class will land into one of these 12 nodes, generating the first Fourier component, denoted F1. This is equivalent to our typical pitch class clock face. If we stretch the elastic around the circle a second time, the pitch classes are stretched further apart, so that now each pitch class is 2 nodes away from its neighbors. We pull the string around the circle a third time, stretching the pitch classes 3 nodes apart, making the F3 component. We continue this process 12 times until all the pitch classes return to their original position. The DFT then returns 12 components, labeled F1, F2, F3, and so on. Mathematically, F0 is trivial for our purposes, so we omit it. Components F7 through F11 are mirror images of F1 through F5. Just as interval cycles 7 through 11 are mirror images of cycles 1 through 5. Since they are redundant, they are also omitted. Using Quinn's imagery of the Fourier balance, we can picture each component as a plate balanced at its center. Every time we add a pitch class to its corresponding node on the plate tilts more in that direction. The direction that the plate tilts is called the phase, and the amount of tilt is its magnitude. To analyze a set of pitch classes with the DFT, we place all the pitch classes from the set around the 6 non-trivial Fourier components and examine the resulting phases and magnitudes. Let's try this out with C major, the key of the people. We represent the pitch classes as an array telling us how many of each pitch class we'll be using. In this case, we'll have just one instance of each. For comparison, we will plot our collection out on the F1 and F5 component circles. We can depict the pitch classes from our array as vectors having both length and direction. We place a vector on the component circle the length of each pitch class's value, in this case 1 unit long and pointing to the pitch class that it represents. Next, we add all of the vectors together by placing them head to tail. The order that we chain the vectors together does not matter because vector addition is both commutative and associative. We draw a new vector from the origin of the circle to the end of our vector chain, and we now have our magnitude and phase data for this collection. The F1 component indicates how chromatically clustered a collection is. From C major's very low magnitude of 0.27, we can say that the diatonic collection is not very chromatically clustered. Indeed, we know that it is minimally chromatic for a septichord. In contrast, the F5 component indicates how fifty a collection is, and from the very high magnitude of 3.73, we can say that the diatonic collection is very fifty, indeed maximally so. Notice that on the F5 component, the resultant vector for C major does not pass through pitch class 0, the tonic. Instead, it passes exactly through the node containing pitch class 2, the point of symmetry for the collection on the F5 component circle. Of course, in music, we rarely see exactly one instance of each pitch class neatly occurring together like this. Rather, some pitch classes will be omitted while others are duplicated. If we account for the number of times each pitch class is present in the passage by using multisets, sets that allow for multiple instances of each element, the phase of the resultant vector will probably not pass quite so cleanly through pitch class 2, but instead somewhere in its vicinity. To simplify the messy data, I introduce a quantizing function that snaps the phase to the nearest node. Passages of tonal music tend to have phases on the flat side of their scale degree too, which means that when the phase quantizes to a particular node, we can infer that the node is the second scale degree for that particular diatonic collection. This means that we can use phase as an indicator of the key of a largely diatonic passage. Or, more accurately, we can use the phase to identify the implied key signature. To process the score, I create a window of a length of a constant number of beats. As the window slides across the score, incrementing by beat, the program performs the DFT on the pitch class content contained within that window. The program can count pitch classes in 3 ways. It can count the number of onsets each pitch class has in the window. It can count the total duration each pitch class has within the window, or it can give a binary yes or no to the question, is this pitch class present, creating a flat set. This process continues until the end of the score, creating a series of overlapping windows in much the same way that a camera takes multiple pictures and stitches them together to create a panoramic photo. The first piece we'll look at is the exposition from the first movement of Mozart's String Quartet No. 4 in C major, K157. This graph shows the magnitudes of all 6 Fourier components in just the exposition. It was generated with a 16-beat sliding window. The mass of lavender represents the F5 component, and its prevalence indicates that perfect fifths, or the measure of diatonicity, is the most salient harmonic quale of this sonic landscape. Since F5 is the most prominent component, let's take a closer look. Here, we see the F5 magnitude extracted from the previous image, overlaid with both the raw phase data and the quantized phase. Since the phase of the F5 component correlates with implied key signature, we can use this information to infer that the piece begins with 0 sharps or flats, indicated by the 60-degree position, and moves to 1 sharp, indicated by the move to 90 degrees, sometime around the 75th window, where it generally remains for the rest of the exposition. In other words, we see the modulation to the dominant reflected by the phase values given by the DFT. And now for something completely different. Messiaen's Theme and Variations for Violin and Piano is one of his early works and adheres strictly to his modes of limited transposition. Looking at just the theme provides us with an opportunity to explore the DFT in a very different harmonic context than the Mozart, though still with well-defined collections of pitch classes. This graph shows the magnitudes of all 6 Fourier components of just the theme. Upon viewing, we can immediately see a 3-part construction of the theme based on which components are the most salient, or have the highest magnitude. The first section is in A prime form, with the triple peaks of the F6 component showing the similarity of the beginnings of the 2 A repetitions most clearly. Both this and the C section use Messiaen's third mode of limited transposition exclusively. The B section employs the octatonic collection, Messiaen's second mode of limited transposition, as its background collection. We'll start by looking at the B section of the theme, where the F4 component dominates. The F4 component is associated with the interval class 3 cycles and the sound of octatonicity. Just like we did with the F5 component in the Mozart, we'll extract the magnitude of the F4 component and overlay the phase and quantized phase. The very high magnitudes of the F4 component, combined with the phase settling at -60 degrees, indicate the presence of the octatonic 0-1 collection, Messiaen's second mode of limited transposition, in much the same way that the position of phase can be used to determine the implied key signature when the F5 component reaches a high magnitude. The octatonic collection has several unusual features when viewed through the DFT. The collection is a prototype of the F4 component, meaning that it has the highest possible magnitude for that component, assuming only one of each constituent pitch class. The octatonic collection is also perfectly balanced, meaning that it has a magnitude of 0 in the F1 component. There is no tilt whatsoever. The octatonic collection has the even rarer property of having a magnitude of 0 in every component except for F4. To demonstrate, we will compare the octatonic collection on the F4 and the F5 component circles. Just like we did with the diatonic collection, we'll plot out the vectors representing each pitch class and then add them together. On the F5 component circle, the vectors form a chain that returns to its origin. This is because every vector has an equal and opposite vector. These are annihilating pairs that cancel each other out when added together. When every single vector has been cancelled out, we are left with a magnitude of 0. In contrast, on the F4 component, the vectors reinforce each other, resulting in the highest possible magnitude for a flat set on the F4 component. While the middle section of the theme is strictly octatonic, The first and third sections adhere to Mession's third mode of limited transposition. For our use, mode 3 can be thought of as a combination of 3 of the 4 augmented triads, interval class 4 cycles, represented by the F3 component. This means that mode 3 includes one of the 2 whole tone collections, interval class 2 cycles, represented by the F6 component, and half of the other. We'll plot the pitch classes of mode 3 onto the F3 and F6 component circles in the same way that we have done with the previous collections. Here we can see that each component has 3 annihilating pairs, which effectively cancels out 6 of the 9 vectors. This leaves just 3 vectors to point in a single direction in each component, giving both F3 and F6 a magnitude of 3 for this collection. The transpositional symmetry of this collection makes it similar to the octatonic collection. It too is perfectly balanced and also has a magnitude of 0 in every component except for F3 and F6. We can confirm the music's adherence to the mode by looking at a panorama generated with the flat set valuation of pitch classes, the one that just asks, is this pitch class present, yes or no? Since Messiaen is strict about his use of modes, there is not much fluctuation in this graph except for when the sliding window overlaps between mode 2 and mode 3 passages. Here, it's hard to see both the F3 and F6 components because they're right on top of each other, so here they are individually. As long as the music is strictly in mode 3, both the F3 and F6 components maintain a consistent magnitude of exactly 3, and the other components are completely absent. The original graph I showed for the piece uses the onset valuation of pitch classes and has many more fluctuations than the flat set. The frequency of notes occurring on the musical surface caused the F6 component to emerge slightly more prominently in the A prime sections of the theme. In the C section, the F6 component is even more pronounced than the F3 component. The implication is that, while still adhering to his third mode of limited transposition, Messiaen actively suppresses the F3 component by generally avoiding repetition of notes from the augmented triad with the pitch classes 3, 7, and 11. Instead, he emphasizes the whole tone subset of mode 3, notes that reinforce each other on the F6 component while canceling each other out on the F3 component. Looking at a panorama made with the total duration valuation of pitch classes, we see still another view of this sonic landscape. Here, the F6 component is more strongly pronounced in the A and A prime sections, and less pronounced, even de-emphasized, in the C section. By looking at the total duration, we are seeing the effects of sustained notes over the course of a passage. In the C section, while notes from the whole tone collection are being repeated and have greater frequency, giving us the high F6 component in the onset graph, rhythmically they occupy much less time than the sustained notes of the augmented triad that reinforces the F3 component and reduces the F6. Choosing to look at different pitch class valuations reveals different aspects of how a composer realizes a backgrounded collection. Examining macroharmonies through the DFT clearly displays a broad overview of a piece's sonic landscape, and it does so in a completely quantifiable and mathematically precise way. These two brief analyses offer a very limited view into this methodology and its capabilities. Many other variants exist. The overview can be as blurred or as granular as the analyst wishes, simply by adjusting the size of the sliding window. Music based on other collections that equally divide the octave is evaluated with as much ease as our 12-note chromatic world, opening the door to examine other understudied repertoires simply by changing the length of the input array. Different modes of listening can be modeled by using the onset or the duration methods of counting pitch classes. Perhaps most significantly, this is a single methodology that is equally applicable to music from a wide variety of genres, time periods, and styles. As long as the music can be encoded with discrete pitches and rhythms, this approach will have something to say about it. Many music analytical techniques are bound to a particular repertoire. The DFT is stylistically and historically agnostic, allowing for a more unified understanding of music writ large.